screen sharing. Okay. Okay. Rearrange these windows. Too many windows. Okay. You can see this screen now properly. Okay. Let's do a very quick recap. So far, we are looking at uh, population dynamics of species which can be written in this form. Okay. Where we can basically assume that entire dynamics can be described in discrete generations. And as we discussed in the class and also in the last lab, a key assumption for this to be true is that the generations must be non-overlapping. Of course, this is one way to ensure these kind of model framework are valid, but there are ways to sort of apply this even when it's not perfectly valid, but this is sort of most important criteria when we are thinking of empirical systems in particular. Okay. So we discussed a couple of models of this type, and the model we discussed was basically a simple logistic model, right? And we discussed various properties of the model, and we discussed general properties like equilibrium, where populations do not change over time, and we find them by solving this equation. Okay, and then we also looked at the idea of stability. Stability means that a perturbation which is small from the equilibrium returns, and basically decays. Therefore, the system returns back to the equilibrium. And we made mathematical derivation and showed that the modulus of f prime at the equilibrium is less than 1, and the system will be in stable equilibrium. Now, so having done this, now let us try to write the couple of very first steps that we did when we wrote down these equations. What was that? We basically said that the number of individuals in generation t plus 1 is number of individuals in the previous generation plus total births, right, minus deaths, right? Okay. And then we wrote this as nt. If b is the number of births per individual and d is the probability of death, then it can be written in this form. This is what it wrote, right? Now let us think about the following. So now one of the reasons why we wrote at one generation time was that we thought of them as non-overlapping generations, right? Okay, now what if we had taken halfway through the generation? Okay, what would this term be if we had done halfway through the generation? If it was not t plus 1, let us say. Let's say from now, let us look at
it will be t minus t by 2
and t plus half. If this is what we were looking at, what would that be? I think it's Amir who said it's nt plus b minus d nt by 2. Is that what you said? Basically, the number of births and deaths will be proportionately small. Is that what you said? Okay, so this is one way to think about the problem, right? And if I look at halfway through, this must be true. Okay,
No, what I meant was B will not be divided by 2.
Why so?
Because we are seeing like everyone is born at the same time, and taking half to A, then everyone has been born.
Okay.
So D will be divided by some factor, I don't know, but B will remain that.
Okay, that's a really good point. Sort of it actually connects back to this assumption. Why this assumption is extremely crucial for sort of to make realistic connections. Okay, the idea is that there are a bunch of individuals. If consider a scenario when the birth happens randomly over time between 2 generations. If that was the case, would this equation have been correct? Then and also likewise, if you assume that the birth deaths were also happening randomly in this one generation, then again this would have been and under the assumption of the fact that the births and deaths were a continuous process over time, this would have been correct, right? This the assumption we made. But if I assume that the generations were strictly non-overlapping, then this will not be correct, right? Then I cannot write it this way. So I have to go back to the previous step. I can make connections between population sizes only across 1 generations, because we said we are looking at a system with non-overlapping generations, right? So that's really important to understand. So now let us consider systems where the assumption of non-overlapping generation is not crucial. In which case, if I were to now take an arbitrary time unit n t plus delta t, and we want to know, given that there were n-t number of individuals, reproducing individuals at time t, what will be the number of individuals at t plus delta t, where delta is an arbitrary number now. So what would that be now? It would be b minus d times nt times dt. So you all agree with this? Basically what this says is that we have reduced 1 generation to an arbitrarily small time unit now, delta t, which is much smaller, which is smaller than 1. So therefore the number of births and deaths will be proportionately small. Is it reasonable? Or at least as an approximation, if not as exact. Is that correct? Okay, so one can actually mathematically argue whether it's strictly correct. It will depend on the kind of process we are assuming. So think about the following, right? At the end of the day, if the real system has a discrete number of individuals, as we know, and the births and deaths are stochastic processes, you cannot determine exactly when those events happen, so they're happening at random times, right? Okay, now so what we are writing is now, in some sense, what is the average population size or an expected population size at a time interval dt from t. Okay, so within that average sense, maybe we can write an equation. Okay, so if we accept that, what we can now do is take nt to the left hand side. Okay, so we now have t, and then we divide both sides by delta t. And then we now take a limit of delta t going to 0. So we just make this time step arbitrarily small. So in that limit, what happens to left hand side? Left hand side is nothing but dn by dt, and right hand side is b minus t times n. So I'm going to change notations now. Okay, so I won't write t as a subscript anymore. I will now write t as in parentheses as a function. So far all okay? Any questions? Okay, and let us denote b minus d by r. So therefore what we have is dt. Let me know if you have any questions before you go to next page.
Sir?
Yeah.
We aren't considering immigration in this model also?
Yes, we are continuing with all the assumptions as before. The only assumption we have now relaxed is that the births and deaths are not happening. Births and deaths now can happen in a continuous way. So they are not staggered, by a generation time in precise sense. So they can happen, or at any arbitrary interval of time. Did we make any other? So we had a bunch of assumptions for the previous model. Apart from that, do you think was there anything else that we relaxed here? No, right? That's the only assumption we have now changed, right?
Yeah.
So we've sort of gone from saying, births and deaths can happen only in a very discrete one generational time scale to the other extreme, where we are now saying births and deaths can happen in an arbitrary small time delta t. Of course, that extreme limit is not going to be biologically meaningful. So we will have to deal with some consequences of that, which means that there's an approximation of that. In real life, especially when we are looking at finite population sizes, births are not going to happen continuously. But if you think of the entire human population on Earth, right, then effectively births and deaths are continuous on really, really tiny time scales, right? Okay. So now let us go to. So let us now study the consequences of such a model. Okay. So we now have, what we call continuous time relation, where Tn by Tt is equal to Rn in the most general form. Okay. So let's consider various cases exactly like we did for the case of discrete time model. What will be the first case that we will consider?
Sigma is less than 1.
What is less than 1?
R is less.
R is less than 1. Okay. Is that what we are doing? Think about it. You're on the close, somewhere close, but not quite. We have to do something
R
more
equals
before.
0.
We should do something before that.
R equals 0.
The equilibrium points are 0.
Sorry?
You mean the equilibrium points before that?
Okay, so if we can think of equilibrium points, that's one interesting way to think about this. Okay, so before we do equilibrium point, there's something more to think about. All of you, or maybe whoever is saying now, has already made some implicit assumption about R.
R should be
R
greater
is
than
not
0.
0.
R is not 0. Okay, that's one assumption. But I can consider any value of R, but there's something more fundamental about R.
R is constant.
Non-negative value.
R is constant. It's not a function of time.
Yeah, okay. So does R has to be constant?
No.
It doesn't have to be constant, right? Just like the capital R in the previous model did not have to be a constant. The small r here, which is basically births minus deaths, in a small unit of time. Okay, doesn't have to be constant. So basically, whenever you write down the model, the first thing you must always check is understand what are the units. So what's the unit of R? It has units of 1 over time, right? It's a growth rate. Do you all agree with that?
Yes.
Okay. So in fact, we can make something more specific. So In fact, growth rate is actually not very accurate. Actually, it suggests it even better than that. What exactly is R? If I were to write an equation for what would that be? It's actually 1 over n times dn by dt. Is that right? Is that correct? Right. So what is dn by dt?
Number of individuals by time. Change.
It's not it's a change. It's a population size change per unit time. Right. Right. So dn by dt is basically says population growth. We agree? N is the entire population size. How is that population size changing with time? It's a population growth rate. So now what is R then? It's the population growth rate divided by N. Right?
Per capita population.
Per capita population. I mean, you don't say per capita, you just say per capita growth rate. And that actually makes perfect sense. Why? Because what was R in the previous slide? It was B minus D. What was B? B is the number of births per individual per unit time. D was the probability of death per unit time, right? Again, for an individual. B and D, small b and small d were both defined for single individuals. Again, if I go back one more slide, when I wrote capital B and capital D, they were defined for the entire population. Capital B was small b times nt, small d was d times nt. Is that fine? So basically, because this was R minus B, sorry. It's not erasing. Okay, I have to deal with it. So since it was just B minus D, both of them were defined for at the level of individuals. Is that fine? So per capita means for an individual. Okay. There's another name for R which you might come across. It's also called specific growth rate. I think there's some difference in how people use the word. So per capita growth rate or specific growth rate is the correct usage. Both of them are correct usage. Okay. Or you can very explicitly say growth rate per individual. Okay. But usually if you just say growth rate, it often means population growth rate. Okay. So be careful when people say growth rate, what exactly to say. Now that's one point. So now, what are the range of values that R can take? So R is basically B minus D, right? What are the range of values that R can take?
Or any real number.
So
Any non-negative number.
So why is it non-negative? So you are saying that birth has to be always greater than or equal to 0? But sorry, are you saying that births are always greater than or equal to deaths?
-1 to 1.
Did you whoever said that it has always to be non-negative? Do you agree it doesn't have to be now?
Yes, sir.
So R can be negative, right? Because it's when B is less than D, and that can happen under resource constraint environment, right? So R can be negative. Of course R can be positive. B greater than D. Now, are there numerical bounds on the values that R can take? Somebody said between -1 and +1. Why? So what's the lower? Let's think of the upper bound. Okay, so if nobody dies, D can be 0, right? What about B? What's the limit for B? It's basically the limit, the number of individuals, number of offspring per individual per unit time, whatever that limit is. It's probably it can be arbitrarily high number depending on the species, but technically there is really no sort of no mathematical bound first. It's entirely driven by whatever the value that the B can take, whatever the maximum value B can take, right? You all agree? Okay.
But for D, there is a like upper bound of 1, so R will be at least -1, right?
That's a very good point. So now let's think about the upper bound. Let's start here. R max limited by B max. Okay. So basically it could be, but it could be in principle a large positive number. Okay. Now what is D? Okay. Now let's think about the minimum, right? Suppose the eraser is Does anyone know why this could happen? Because sometimes I just have to close and open this. But anyway, I will let me write it this way. So now what about the minimum limit? So now B, when there are no births, then the R minimum basically will be now given by minus D maximum. We all agree? R minimum is minus D max. Okay. So what's the maximum D can take? So in the previous formulation, which is a discrete generation formulation, the maximum that D could take was 1, right? Now the moment you make it continuous, okay, now what happens to probabilities when you go from probability mass functions? Probability mass functions have a limit of, for any given value has to be less than 1, or maximum can be 1, right? But the moment you go to probability density functions, is there a limit to it? The moment you make them continuous, what's the maximum value it can take?
There's no limit.
There is no limit. So basically, there is really technically, again, it's mathematically there is no limit that the D has to be 1. D can be now much more than 1, because what must be less than 1 is what happens in a given time interval. If a time interval is delta t, the probability in the time interval must be less than 1, but D is now per unit time, right? So that can be arbitrarily large also mathematically. So basically, to summarize, basically both these limits can be arbitrarily large, and therefore mathematically what we arrive at basically is that R has to be less than minus infinity, greater than minus infinity, it can go all the way to plus infinity in principle. Okay, and of course the maximum limit will be bounded not by the actual species themselves. Is it fine now? So this is one fundamental difference between the R in the continuous time model and the capital R naught that we were writing in the the discrete time model.
Sir.
Yeah.
What is the dimension of B and what is the dimension of D?
B and D.
Yes, sir.
It's per unit time.
Per
Both
unit
of them are
time.
per unit time. Yeah. The rates.
So, if I remember, when we were talking about D, it was supposed to be a probability of death. So probability cannot have a dimension, right?
No, but it was defined for one generation, right? Probabilities do have a, when you are defining things that can happen repeatedly, okay, you do define it. You define it per event, right? Let's say if I toss a coin, you say that probability of getting head is half for this event, right? But so there's always that implicit unit of per event. So here the event length was 1 generation. Therefore, there was the unit time even in the previous formulation.
Right, and with small b, there is something similar going.
Exactly, both of them are per unit. So in the previous instance, it was per generation, exactly, but now it's more generally per unit time.
So, sir, if D is probability per unit time, so probability can't be more than 1.
So that's what I mentioned. The moment you go from discrete to continuous regime, probabilities can become arbitrarily large.
Oh,
So
okay.
what needs to be less than 1 is probability in a given time interval. For example, let me give an example. No, so what is this? Suddenly something funny happened. Okay, I'm going to skip this page. Okay, so think of this simple example. Let's say there are let's say I have 5 numbers between 0 and 1. 1/4, half, 3/4, and 1. Okay, let's say there are only four numbers between 0 and 1. What's the probability of picking any of them? It's 1/5, right? For each number, right? So now consider a real line. Okay, between 0 and 1. What's the probability of picking any number between 0 and 1? That will be 0.
1.
Right? Probability of picking now half. If I were to say probability of the number that I picked between 0 and 1 is equal to any arbitrary number is actually 0. It could be even true for half, 1/4, and everything. So a lot of notions of a probability. So now think of basic rule that you know about probability. If we add up all the probabilities, it must always add up to 1, right? Okay, but probability of picking any number is 0 between 0 and 1. So if you add lots of zeros, we'll get zeros, right? But that can't be true. Okay, now therefore, so our classic notions of discrete probabilities just break down when you go from discrete event space to a continuous space. So what you now do is you don't ask what is the probability of half. Let's say X was a random number. If you say this will be 0, but so you won't ask this question anymore. What you do is you ask what is this probability? Probability that I get a number X, a number in the interval X and X plus Dx. So this now becomes a probable, sort of, a measurable probability. And you want to ensure this number is actually less than. So, so this requires you to sort of, go to sort of, some fairly deep mathematics, which I'm totally unfamiliar with, called measure theory. So that really helps you resolve all these issues with probability. So probability densities, that is defined for continuous variables can be 0, can be infinitely large, but this will still be bounded by sort of normal intuition of probabilities. So which is why again D now, because we are now looking at continuous time intervals, can become infinitely large if you think of infinitely small time. Okay. So I hope that sort of partly resolves your. I have no idea why it got split into 2 different slides. Okay. Let me open a new page and just label these. 4. Let me maybe unshare and share back, because that might be the sometimes that just works. It is a mostly split. Okay. So let's now go back to where we were, which was this one. Okay. So let me write that equation again. dn by dt is equal to Rn. I hope all understand what is this small r now. Remember that was the values can now be negative, which was entirely ruled out for the capital R, right? Because see, one fundamental difference between the small r and the capital R is capital R also included the current population. Okay, so the current population plus the change, that together cannot be negative. Okay, and also the capital R was also telling you what will be the next generation. That again cannot be negative. whereas the small r is telling more about the changes, but the changes can be negative or positive. So therefore, this difference between small r and the capital R. Okay. So now let's consider the case I wanted to consider, which is what's the first case we considered in the discrete time model. What did we assume about R? We considered the case of R is equal to constant. What does that mean? Biologically, it means unlimited resource. Okay. So what happens in that case? Now this equation can actually be solved. Okay, so I will not solve that. I'm going to assume you know the solution. In fact, I had sent an email asking you to just revise that. So solution of this equation is
When you say unlimited resources, this is an R is positive, is it? Or
oh, that's a good point. Yes. Okay, sorry. So maybe I shouldn't say unlimited resources. Is that right? I should just assume that the per capita resources are constant. Okay. So should I say unchanging resource? Is that better?
I think unchanging per capita resource.
Yeah. I mean, then that's that's just saying in words.
The population size will change. No?
Let's not do this. Let me erase this. Okay. And now, but the solution will be still here. This is fine. Okay. So now here we can consider two cases, right? One is R positive. That corresponds to unlimited resource. Is that fine, Amir? That's a good catch. Thank you.
Yes.
That means that we will have exponential growth. And the alternative is R is negative. That means I know constant. It's not only limited, it is actually constant limited resource. Is that fine? Or we can say insufficient. It's constant, but it's insufficient. So what do we get in that case? R negative. That will lead to extinction. Any questions on this slide? Case 1. So we again have the classic two results, which is either an exponential growth or an extinction. Is it fine? Okay, if it's fine, let's go to a new page now. And these results so far are consistent with what we have found with discrete generations. Is that correct? So far, we haven't added any new insight to this. So can happen continuously, hasn't changed our results so far in the regime of constant per capita resource. Okay. Now let's consider case of intraspecific competition again. So how do we incorporate intraspecific competition? So again, remember what you did last time. So that capital R, let me just write here. Recall what we did. We wrote down capital R as a function of n, right? Okay, now when we said this actually decays linearly, that was the model we considered, and the case that doesn't decay linearly was this, right? We had two cases. This was case 1, this was case 2 for the discrete time. So what's the equivalent we will do now? We will consider intraspecific competition. We think what is the impact? The impact on that of the competition will be that as the number of individuals will increase, the per capita growth rate reduces. So we'll now plot R as a function of n. So that means we assume that R is not a constant anymore. R is a function of n. Okay. So again, the previous scenario was R was a constant, right? So which led to either exponential growth or exponential, for example, if it was if R was a negative value, this was explosion. So let us now consider a more realistic scenario, which is that we do have good amount of resources when the population size is small. So therefore, the per capita growth rate is high, but it declines with n. Okay, so per capita growth rate declines with population size. So what is the simplest mathematical function that we can consider now? It will again be linear. Okay. Okay, let's assume the value is R0 when n is 0, and then let's assume that at value k it crosses 0. Is that fine? Is there a simpler function than monotonically linearly decreasing function of R0 of the specific growth rate? No, right? Okay. So now let's write down this. So we have done this in the past, so I'm not going to spend too much time on this. So R will be R0 times 1 minus n by k. Is that fine? So when n is equal to 0, the per capita growth rate is R0, and when n is equal to k, per capita growth rate is 0, right? Now here is the thing. What happens when n is greater than k? Is that allowed in this model?
Yes, sir. We'll have a negative coefficient, so charge decay at that point.
Yes, you're right. So because when n is greater than 0, R becomes negative, which is allowed. Is that right? Okay, so there is indeed allowed here. So we can, so there is no constraint on n has to be less than k. So a lot of the constraints we had from the previous model, they're all now not required anymore. Okay. So let us now write down. So any questions before I go forward? So we have now written down how to incorporate intra-specific competition in the specific growth rate or the per capita growth rate. All fine so far? Let's now move on.
Sir,
Yeah, please.
with respect to like the intraspecific competition, does it necessarily have to be intraspecific competition, or it could be any other factor also?
It could be other factors, but let us now focus on competition. Is that fine?
Yeah, and for like case 1, why didn't you consider the R equal to 0 case? I mean, as a
Or a
sub
constant can be a 0 or is equal to 0 also. It would just be a very trivial solution, right? If R is 0, what happens? Right hand side is 0. So dn by dt will be 0, right? So I can also write that down here. So R is equal to 0 implies dn by dt is 0 implies n is equal to some constant. So whatever the value it's there, just stay there. Is that fine?
Yes, sir.
Okay, so let us now write down the model now. So which other type of processes can lead to a value, a sort of functional form of R that declines its own population size? Because you asked me, one of you asked me, why are you considering only intraspecific competition?
Predator.
predator. Why? Why presence of predator? Because of predator, this should go down. So what is this curve? What is the meaning of this curve, right? Think about it. What's the meaning of this curve? The the growth rate of an individual, which includes the number of offspring that it will produce minus its own death rate, right? That's a growth rate, right? Individual growth, next population, that declines with the population size itself. Which other can predation cause something like this?
Yeah, but in predation, for example, it can happen because when the prey is in very large in number, I assume when the population is very large in number, the predator has an easier time catching prey. When they're sparse and rare, like in a desert or a very sparse landscape, finding prey is hard. Therefore, the predation or the predation pressure is lower. Like in a naive example, for example.
May I know your name, please?
Pavan.
Pavan, okay. So just think, it's actually a very interesting point you make. Let's think about 100 individuals versus 10 individuals. Okay, a predator arrives now and will eat one individual. Okay, so what's the death rate if you are in a group of 100? What's the probability of death for this specific event?
1 in 100.
If you are in a population size of 10, what would that be?
1 in 10.
Which is higher?
1 in 10. Yes.
Must be the opposite pattern.
By that logic, I agree. But I was imagining more from an organismal perspective. When prey is abundant, it's not. You are assuming that the it's consuming one.
No, you're looking at the prey. No, you're assuming a predator perspective. But R is for the prey here, though.
Yes, but on an absolute number, isn't the absolute value of D higher when the N is higher, simply because the predator can hunt more? That's all. Because here I'm assuming the predation is a function of N, which we are completely ignoring because we're looking from the prey perspective. So I agree from that aspect. But I was just giving you an example. But I see your point.
I just want the example to work. I didn't understand how the example actually is correct, though. How it will lead to a graph like this. I mean, it's possible, but I just don't understand how it can lead to a graph like this. So increasing the number of prey will increase the predation. Is that what you're saying?
To some degree, yes.
Not clear how. Not clear how.
Okay, go on.
Distinguish the number of prey who will die versus the risk to a specific individual. See, R is risk to a specific individual. It is actually, so you're absolutely right that as the number of prey increase, it's easy for a predator to find one individual. But it is still possible that prey is safer in a larger group. Both of them can be true.
Yes, yes.
So we have to show that the second one is not true. Then only this.
Yeah, it depends on the strength of strength from collectivity, like being in a collective and herd.
But you made the calculation.
I don't make a calculation. I'm saying in one extreme corner case, the predator efficiency increases with population, but that's not necessarily true always.
Yeah,
I agree with you.
Okay, so actually, basically getting this pattern from predation is not very obvious. I mean, it's possible it can make somehow work, but it's not very obvious at all.
That's right. I concede.
Any other ways? Any process other than intraspecific competition that can lead to this?
Something like a disease, like a lethal disease, which is, getting into the population.
Okay. So why will the growth rate depend on the population size?
So it'll be something of this sort, right? Like the number of deaths due to the disease is going to be directly proportional to the population size.
The number of deaths, but this is the death per individual.
The transmission
y-axis. The y-axis is death per individual.
So the transmission rate might be higher with higher death.
So basically, you're assuming that as the number of individuals increase, they all herd together, therefore the spread increases. So you're assuming that the transmission rate between individuals goes up with the increasing population size. Therefore, yeah, that's one way it's possible. Yes, I agree.
But Vishu, isn't this the same as like, it goes up faster, but goes up faster than the
Exactly,
rate
it
at
has to
which
go much faster than what this
the
can do.
decline
Yeah.
by collective, like decline by n.
So there is a small difference between a disease and a predator, right? Predator is happy eating usually one at a time. Right?
But then there can be
but the
more
virus,
predators also.
Yeah, you're right. If you add more predators, you're right. You can make things slightly more complex. So you have to work hard to make it complex in a predator case. But I think it's much easier for a disease or a parasite to spread from one to the other because
and that also leads the other that other leads to the oscillation kind of a thing, I guess, not such a straight line.
Yeah. So it won't lead to something as simple as, but the parasite in principle, if the transmissibility is much larger than the increased risk to individuals. Yes, you're right. Yeah, that's one possible way.
Not just the transmission thing about diseases. In general, if we have more population in the same area or same resource amount, we have more likely to develop diseases. So
why?
I mean, you have if you have a lot more population close together, it's quite likely unsanitary conditions and stuff. So you could develop more diseases and more fatalities.
Not very evident.
True.
Okay, it is in some processes, but yeah. But even the one that Thomas suggested, it's not very evident. But as the numbers increase, the disease will spread much faster. It's also not very clear. There are a lot of many counteracting effects there. But I guess one can somehow make both the predation and parasites, they are similar in many ways, but they're also very different in some ways. But in parasites, the numbers are often much larger. Therefore, usually, when you go from predator, one trophic level to the higher trophic level, the numbers reduce dramatically, right? So therefore, the predation argument is much harder to make. On the other hand, if it's parasite, they because the way they grow and the way they transmit is a bit different. Because in that case, they can work slightly differently, and where there's something like that might be actually in principle possible. Okay, anyway, sorry, cannibalism. But cannibalism is related to resources in some ways. So yeah. Okay. So anyway, so let's move on now. Let's move on to this now. So we have now arrived at continuous time model with intra-specific competition, and this is also called logistic model. Okay. So in fact, technically speaking, this is the correct logistic model. Okay. Okay. I won't go into detail of why it is so, but to make sure we don't get confused, we will refer to this as continuous time logistic model. Is that fine? And the previous one has the discrete time logistic model. So we will use this distinction. The previous one in the mathematics literature is also called logistic map. Okay, so that's another way to distinguish the two. But the simpler way might be continuous time model versus the discrete time model. Okay. Okay. Now, so we have now written down the model. Now we have to understand what does the model say about how populations change over time, right? So now again, the concept of equilibrium is again quite useful here. So let's see how we can define equilibrium. So what is equilibrium? When the population doesn't change with time. So in this equation, what does that mean? Population doesn't change with time.
Or n equal to k.
N by dt is 0.
So the fundamental principle is the left hand side is equal to 0, right? dn by dt is equal to, let's write a general equation now. F of n is equal to 0. Is that fine? So if you now ask how do you find equilibrium, basically solve f of, let's call that as n star, okay, like previously. Solve all the roots of this simple equation, f n star is equal to 0. Then you get all the equilibrium values. Okay, so shall we do that for the logistic model now? So if we now set what do we get? We get n is equal to 0 or n is equal to k. So basically this can be 0 or this can be 0. Is it fine? If the first n itself is 0, then that's one equilibrium. And if the second term 1 minus n by k is 0, then that will yield us n star is equal to k. Is that fine? Again, notice the difference. In the previous model, there was an R0 dependence, capital R0 dependence, right? That's now gone. So capital K now becomes an equilibrium. So this corresponds to extinction. This corresponds to a finite size population. Is that fine? Any questions on this page? Let's move on. So what is the next thing? So next so what's the thing we did after finding stability? Oh, sorry, equilibrium. I told you the answer, sorry. So after finding equilibrium, we looked at the idea of stability. The same definition can be used now. You know, if a perturbation decays, that would be a stable equilibrium. If a perturbation grows, it would be unstable. Okay, so now for an equation of this type, the condition for stability is basically find again the slope of the function at the equilibrium values and check if it is less than 0. If it is less than 0, it is stable. If greater than 0, unstable. Does that make intuitive sense why it is correct?
One also. Shouldn't it be 1? I don't know.
Okay, so let's go back. Let's go back and understand this. Okay, so I can of course do the derivation, but let's think intuitively. Let's go back to the case. The idea of stability equilibrium is as follows. The stability of equilibrium is as follows. We know that for the constant population says what happens if R is greater than 0, you have exponential growth. Is that right? If R is less than 0, you have extinction. Is that right? The per capita growth rate, if it is positive, then we have exponential growth. Per capita is less than 0, you have extinction. All of us agree with that, right? So the idea of finding a stability of equilibrium is that what is the R? What is the R for the perturbation you made near the equilibrium? So basically, that turns out to be same as this F prime n star. Okay. So it's basically what is F prime n star? F prime n star is the growth rate of per capita growth rate of the perturbation that you have made. So for that perturbation to grow, what must happen? It has to be positive, right? So therefore, this leads to unstable equilibrium, whereas a negative value of F prime n star is stability. Does that intuition make sense? So one way to think about this, intuitively is that again, there is actually a lot of parallel with what we did in the discrete case also. In the discrete case, in the discrete population case when R was constant, consider the discrete model, discrete time.
Vishnu, I just have a doubt. Should it be 0 or 1, that differential?
Which one, sorry?
The previous page. Table is less than 1.
Where is the table?
The stability. It's less than 1. It's stable or 0?
It's actually less than 0.
I don't understand how that came.
Yeah, so I can explain to you intuitively. Let's go back to the discrete time scenario, okay? And the simplest case we had was R times NT, right? Is that fine? So in this case, what happened? NT plus 1 was equal to R power T NT, N or N1. Is that right? So therefore, we said R greater than 1 leads to explosion. Is that right? R less than 1 leads to extinction. Do you all remember this now? Okay, for R constant. This is for R constant. Now for a general case, what happened? There is some equilibrium n star, and we said that f prime of n star must be less than 1 for stability, must be greater than 1 for unstable. Is that right? Now, do you see the parallel between these two?
Yes.
Right? Basically, f prime in the discrete model is equivalent to sort of converting to a, taking the equilibrium and you have made a perturbation. We are now looking at the perturbation, how it is growing. See, capital R was something like, basically you take some value and I'm multiplying it with the R, right? If the multiplication was greater than 1, it will just blow up. For less than 1, it will just, decay in the discrete time case, right? So R was to be seen that way. And if you now take a general case and an equilibrium n star, f prime n star was basically the growth factor for the perturbation. By what factor it is the perturbation is getting changed. If it is growing less than 1, that means the perturbations are dying, therefore it's stable. Now, for the continuous time, because we are looking at the equation form is different now, right? It's actually n dot. The left hand side is the rate of change, right? So here again, if you consider the constant R case, we had these two cases. R greater than 0 is explosion, which is sort of unstable. This is extinction for the constant case. Now, if you now look at the general case, n star will be the equilibrium now. So f prime of n star becomes like basically it's now the per capita growth rate for the perturbations. So therefore, if this is greater than 0, that means perturbation grows. If this is less than 0, that means perturbation decays. Does that make sense? I know some of you will need to leave now because you have a class, but feel free to leave. I can answer the questions that others may have. Any questions on this? The connections between the discrete time and the continuous time. And basically the simple R constant case gives some hint on how these two methods work. The constant case and the stability criterion, they sort of go together. Can sort of make connections here.
One doubt.
Yeah.
In the last case of my continuous time, f dash of n star, you said if it's less than 0, it's the perturbation decay. So, but if f dash of n star is less than 0, isn't it's not an equilibrium state, because by equilibrium state we defined it to be f dash of n is equal to n star. So
what is equilibrium?
The dn by dt is 0. So
That
f
means
dash.
f of n is 0. That's
Okay, fine. So,
the stability looks at the derivatives.
Okay.
Is it clear now?
Oh yes, yes.
Okay, so let me those of you who can stay, please stay back. Others can watch the videos later. Just for the sake of completion, let's do a derivation. I think that will just maybe solve confusions that you may have. Okay, derivation of stability. Okay, so let's start with again n dot is equal to f of n, where we find equilibrium n star by solving this equation. Okay, so what we now do is consider n, which is equilibrium with a small perturbation n. Is that fine? So I'm looking at the equilibrium value, and then I have made a small perturbation, small n, to this equilibrium. Okay, so if I had begun at n star, the system would have stayed there forever. But now let's say I'm beginning at n star plus n. Okay, now let's see what happens. So now, as we do know, dn by dt is equal to f of n, right? So what is n for us? N is given by n star plus n, small n. So if I take the derivative of the entire equation, what do I get? The right hand side, the first term will go to 0 because it's a constant, but the second term will not. So on the left hand side we have this. Is that fine? The right hand side we have f of n star plus n. Is that fine? Any questions so far? So what I'm looking at is I'm looking at a perturbation from the equilibrium. So basically this is perturbation n from equilibrium and star. I'm now looking at how this perturbation changes over time. Okay, now the next step will be to do what is called the Taylor series expansion. Okay, so if you do the Taylor series expansion, so you can write this as f of n star plus n times f prime of n star plus n square by 2 factorial f double prime n star and so on. Is it fine? Okay, now what happens? Now the first term, what is the first term by the way? Because n star is in equilibrium, f of n star is 0. So this is 0. Okay. Now n is a small perturbation. Let us consider the limit of small perturbation. Then n square will be a much smaller term compared to n. So therefore, we can approximate this equation just by the first term. Is that fine? Any questions on this? Please let me know. So is there anybody here who has never read Taylor series? I thought I had asked TAs to just introduce you either in the class or via some tutorials I have suggested online. Okay, so it's actually totally fine to say this is a mathematical derivation I don't need to learn. And in fact, I don't expect that you learn this derivation in this class. So if you think this is a mathematical detail that is too much for my background, that's totally fine. The focus of this course is not to be doing these kind of calculations. So it's only for those who are interested to know how we arrived at the criterion. Okay. So it's, if you're unable to follow this, don't worry. No? But the basic idea of the Taylor series is that if I know a value at some location n star, I can construct what is happening around it by successive derivatives, by looking at lots of derivatives near that point. And I can actually get a fairly accurate representation by just knowing the derivative at that point. That's the basic idea. Let's go to the next page now. So, so if you don't understand this, don't worry at all. So now dn by dt is equal to n times f prime n star. Okay. Now this is basically the simple equation, right? The simple differential equation for which the solution n of t n0 e power alpha t, where alpha is equal to f prime n star. So instead of writing this big thing on the e power exponent, I have written alpha. Therefore, alpha is nothing but f prime n star. So fine. Okay. So this is an exponential equation, right? So there is some initial value of perturbation n0. Okay. How is it changing over time? So it says that it's exponentially changing. The question whether it is increasing or decreasing depends entirely on alpha. So what happens if alpha is greater than 0? The perturbation eta, the nt, goes up. You right? Is that right? What do you say when the perturbation goes up? You say the equilibrium is unstable. Alpha less than 0 means this is negative, and an exponent with a negative on the top would mean things will decay. This means, so basically that gives us the criterion. Okay. Which is why I said that f prime n star is basically like the per capita growth rate of the perturbation. Okay, and we know that when the per capita growth rate is positive, things will increase. The per capita growth rate is negative, things will decrease. So therefore, that forms a criterion for stability. Okay, so you just need to know how to use. If the summary of what you need to know is basically this. It's somewhere in this page. Okay, this is what you need to know. So equilibrium are identified by setting f of n star to 0, and stability is found by computing f prime at n star and seeing if it's positive or negative. Okay, any questions? So I'm going to stop the sharing now. So if you have any questions, let me know. If not, we will meet on Friday at 2 p.m. I'll stay for a few more minutes if any of you have questions.